Okay, welcome everybody. Mark, can you take down the volume just a little bit? It's booming a little bit. So welcome to 6172. My name is Charles Leiserson, and I am one of the two lecturers this term. The other is Professor Julian Shun. We're both in EECS and in CSAIL on the 7th floor of the Gates building. If you don't know it, you are in performance engineering of software systems. So if this is if you found yourself in the wrong place, now's the time to exit. I want to start today by talking a little bit about why we do performance engineering. And then I'll do a little bit of administration, and then sort of dive into sort of a case study that'll give you a good sense of some of the things that we're going to do during the term. I put the administration in the middle because it's like if from me telling you about the course, you don't want to do the course, then it's like, why should you listen to the administration, right? It's like, so let's just dive right in, okay? So the first thing to always understand whenever you're doing something is a perspective on your on what matters in what you're doing. So we're going to study the whole term. We're going to do software performance engineering, and so this is kind of interesting because it turns out that performance is usually not at the top of what people are interested in when they're building software. Okay? What are some of the things that are more important than than performance? Yeah. Deadlines. Good. Cost. Correctness. Extensibility. Yeah, I mean, we could go on and on. I think that you folks could probably make a pretty long list. I made a short list of all the kinds of things that are more important than performance. So then, if programmers are so willing to sacrifice performance for these properties, why do we study performance? Okay, so this is kind of a bit of a paradox and a bit of a puzzle. Why do you study something that clearly isn't at the top of the list of what most people care about when they're developing software? I think the answer to that is that performance is the currency of computing. Okay, you use performance to buy these other properties. So you'll say something like, gee, I want to make it easy to program, and so therefore I'm willing to sacrifice some performance to make something easy to program. Or I'm willing to sacrifice some performance to make sure that my system is secure. Okay, and all those things come out of your performance budget. And clearly, if performance degrades too far, your stuff becomes unusable. Okay? When I talk with people with programmers, and I say, people are fond of saying, "Oh, performance, you do performance. Performance doesn't matter. I never think about it." Then I talk with people who use computers, and I ask, "What's your main complaint about the computing systems you use?" The answer: too slow. Okay, so it's interesting whether you're the producer or the whatever, but the real answer is that performance is like currency. It's something you spend. I would rather have, if you look, would I rather have $100 or a gallon of water? Well, water is indispensable to life. There's circumstances, certainly, where I would prefer to have the water, okay, than $100. Okay, but in our modern society, I can buy water for much less than $100. Okay, so even though water is essential to life and far more important than money, money is a currency, and so I prefer to have the money because I can just buy the things I need. And that's the same kind of analogy of performance. It has no intrinsic value, but it contributes to things. You can use it to buy things that you care about, like usability or testability or what have you. Okay. Now, In the early days of computing, software performance engineering was common because machine resources were limited. If you look at these machines from 1964 to 1977, I mean, look at how many bytes they have on them, right? In 64, there is a computer with 524 kilobytes. Okay, that was a big machine back then. That's kilobytes. That's not megabytes. That's not gigabytes. That's kilobytes. Okay, and many programs would strain the machine resources. Okay, the clock rate for that machine was 33 kilohertz. What's a typical clock rate today? About what? 4 gigahertz, 3 gigahertz, 2 gigahertz, somewhere up there. Yeah, somewhere in that range, okay? And here they were operating with kilohertz. So many programs would not fit without intense performance engineering. And one of the things also that there's a lot of sayings that came out of that era. Donald Knuth, who's one of the Turing Award winner, absolutely fabulous computer scientists in all respects, wrote, "Premature optimization is the root of all evil." And I invite you, by the way, to look that quote up because it's actually taken out of context. Okay, so trying to optimize stuff too early, he was worried about. Okay, Bill Wolf, who designed the Bliss language and worked on the PDP-11 and such, said more computing sins are committed in the name of efficiency without necessarily achieving it than for any other single reason, including blind stupidity. Okay? And Michael Jackson said the first rule of program optimization, don't do it. Second rule of program optimization, for experts only, don't do it yet. Okay, so everybody warning away, because when you start trying to make things fast, your code becomes unreadable. Okay, making code that is readable and fast, now that's where the art is, and hopefully we'll learn a little bit about doing that. Okay, and indeed there was no real point in working too hard on performance engineering for many years. If you look at technology scaling and you look at how many transistors are on various processor designs, up until about 2004, we had Moore's law in full throttle, okay, with chip densities doubling every 2 years, and really quite amazing. And along with that, as they shrunk the dimensions of chips, because by miniaturization, the clock speed would go up correspondingly as well. And so if you found something was too slow, wait a couple of years. Okay? Wait a couple of years, it'll be faster. Okay? And so there wasn't, you know, if you're going to do something with software and make your software ugly, that really wasn't a real, you know, wasn't a real good payoff compared to just simply waiting around. And in that era, there was something called Dennard scaling, where, which allowed things to, as things shrunk, allowed the clock speeds to get larger, basically by reducing power. You could reduce power and still keep everything fast. And we'll talk about that in a minute. So if you look at what happened from 1977 to 2004, here are Apple computers with similar price tags, and you can see the clock rate really just skyrocketed. 1 megahertz, 400 megahertz, 1.8 gigahertz, okay? And the data paths went from 8 bits to 30 to 64. The memory correspondingly grow. Cost, approximately the same. And that's the legacy from Moore's law and the tremendous advances in semiconductor technology. And so until 2004, Moore's law and the scaling of clock frequency, so-called Dennard scaling, was essentially a printing press for the currency of performance. Okay, you didn't have to do anything. You just made the hardware go faster. Very easy. Very, and all that came to an end. Well, some of it came to an end in 2004, when clock speeds plateaued. Okay, so if you look at this around 2005, you can see all the speeds we hit, 2 to 4 gigahertz, and we have not been able to make chips go faster than that in any practical way since then. But the densities have kept going great. Now, the reason that the clock speed flattened was because of power density. And this is a slide from Intel from that era, looking at the growth of power density. And what they were projecting was that the junction temperatures of the transistors on the chip, if they just keep scaling the way they had been scaling, would start to approach, first of all, the temperature of a nuclear reactor, then the temperature of a rocket nozzle, and then the sun's surface, okay? So we're not going to build little technology that cools that very well. And even if you could solve it for a little bit, the writing was on the wall. We cannot scale clock frequencies anymore. The reason for that is that originally clock frequency was scaled assuming that most of the power was dynamic power, which was going when you switched the circuit. And what happened as we kept reducing that is something that used to be in the noise, namely the leakage currents, okay, started to become significant, to the point where now today the dynamic power is far less of a concern than the static power from just the circuit sitting there leaking. When you miniaturize, you can't stop that effect from happening. So what did the vendors do in 2004 and 2005 and since? Is they said, oh, gosh, we've got all these transistors to use, but we can't use the transistors to make stuff run faster. So what they did is they introduced parallelism in the form of multi-core processors. They put more than one processing core in a chip. And to scale performance, they would have multiple cores, and each generation of Moore's Law now was potentially doubling the number of cores. And so if you look at what happened for processor cores, you see that around 2004, 2005, we started to get multiple processing cores per chip, to the extent that today it's basically impossible to find a single core chip for a laptop or a workstation or whatever. Everything is multi-core. You can't buy just one. You have to buy a parallel processor. And so the impact of that was that performance was no longer free. You couldn't just speed up the hardware. Now, if you wanted to use that potential, you had to do parallel programming, and that's not something that anybody in the industry really had done. So today, there are a lot of other things that happen in that intervening time. We got vector units as common parts of our machines. We got GPUs. We got steeper cache hierarchies. We have configurable logic on some machines and so forth. And now it's up to the software to adapt to it. And so although we don't want to have to deal with performance, today you have to deal with performance. And in your lifetimes, you will have to deal with performance, okay, in software if you're going to have effective software, okay? You can see what happened also. This is a study that we did looking at software bugs in a variety of open source projects where they're mentioning the word performance. And you can see that in 2004, the numbers start going up. You know, some of them it's not as convincing for some things as others, but generally there's a trend of after 2004, people started worrying more about performance. If you look at software developer jobs, you know, as of around, you know, early, mid-2000s, 2000s, I guess. Okay, you see once again, the mention of performance in jobs is going up. And anecdotally, I can tell you, I had one student who came to me after the spring after he'd taken 6172, and he said, you know, I went and I applied for 5 jobs, and every job asked me, at every job interview, they asked me a question I couldn't have answered if I hadn't taken 6172. And I got 5 offers. Okay, and when I compared those offers, they tended to be 20 to 30% larger than people who are just web monkeys. Okay, so anyway, that's not to say that you should necessarily take this class, okay? But I just want to point out that what we're going to learn is going to be interesting from a practical point of view, i.e. your futures, okay, as well as theoretical points of view and technical points of view, okay? So modern processors are really complicated, and the big question is, how do we write software to use that modern hardware efficiently? Okay? So that's what the course is about. So anybody wants to leave, now's a good time to leave, because I'm going to talk about administration. Okay? Any questions before we go on? Okay, there'll be plenty of time. So generally, Julian and I will hang around here after class for anybody to talk with us they want. We also will offer office hours with the TAs every week, and we'll get into that. So if you could pick up the sheet that says course information, I'd like to just run through that relatively quickly with you. Okay. So the immediate action items is there is a recitation tomorrow. There are 4 recitations that are listed in section 6. Pick any one and go to it. Ignore whatever the registrar has assigned you. Those are completely inoperative, okay? You want to complete homework 1 by Monday. Homework 1 is basically just getting we're going to use the Amazon cloud for our computing this term. And it's basically just getting you up to speed on using the cloud. Okay, it's very, very simple, and getting you registered for the course. And then in addition, if you've never seen C before and don't feel you can master it, we will have an optional presentation on Sunday from 2 to 4 p.m. right here in talking with an introduction to the C language. Okay? Because C will be the language we use for the course. The prerequisites for this class are 6004, 6006, and 6031, or for those of you who are sufficiently tenured at MIT, 6005, okay? So this is a capstone course. It's taking from algorithms, from software, from hardware in order to do things. So you're going to integrate the knowledge of those 3 domains. If you take a look at the staff, I introduced Professor Shun. In addition, we have 5 teaching assistants and 4 undergraduate teaching assistants. Could the TAs and UTAs all stand up? UTAs I don't think are here, but the TAs are. So here, these are your recitation instructors. Okay? They're really good, let me tell you. We're going to be using learning modules for distributing stuff, Google Calendar and Piazza. Most of you should be familiar with those things from previous courses. There's a bit of a description if you need to do that. So lectures are here. Everything that we do in the class is fair game for quizzes and homeworks and stuff. You know, there's nothing that is off limits in terms of what we cover. Recitations are typically 2 hours on Friday. Typically, they are 2 hours on Fridays. Okay. Part of homework 1 will be signing up for a recitation. One of the things I should mention is that this is a class that is an 18-unit class. Is anybody unaware that this was 18 units? Okay. And so you will spend 18 hours a week on this class. We do everything we can. I have this theory, which is it's not so much how hard a class is, but rather how much you learn for how much you work. So we have a really good ratio. There used to be a ratio they had in the course evaluations called CUMES per tooling hour. So CUMES were a fictitious measure of it comes from acumen, you know, a fictitious measure of knowledge. And tooling hour, of course, is how, you know, working for an hour. And so they used to rate the courses in cums per tooling hour where there was a, some sort of standard scale, it's the 7-point scale. Is this a lot more, a lot less, or whatever? And it was really good because it identified those courses which were simply hard and you didn't learn anything from those that were hard and you learned something, okay? I think although they no longer take that measurement, this class has got a lot of cums per tooling hour, okay? So we'll have office hours on Sunday through Wednesday in the evenings, 5 to 8. You can also make appointments with your TA if you need to meet, if those are not convenient times. Each assignment describes how you'll be graded. There's sort of a little bit of a rubric on the next page, on page 4, showing what the breakdown is. There's 10 weekly homeworks. There's quizzes, 2 of them, which you should put down in your calendar. In fact, we keep a calendar that you can import, a Google Calendar. There are 4 projects, of which the first 3 are worth 10 or 12%, and the last one is the big one. That's worth 24%. And then class participation. Class participation includes making posts on Piazza, okay? I'm not a big fan of giving people extensions, but my staff found a way of making an extension policy that would be palatable to me. The reason is because it's like, okay, suppose that I say, oh, sorry, I didn't get the problem set ready on time. I'll hand it in 3 days later, give it out 3 days later. Oh, and by the way, still due at the same time. You guys would be justifiably, it's like a real hassle, right? So likewise, when you guys hand in things late, it's kind of a hassle for us. So the project deadlines, the coding deadlines, those there's no extensions for. You have to get them done on time, okay? But for a lot of the other things, like the homework assignments and such, we're going to have 3 days that you can apply to get an extension on any of those. In addition, if you and your teammates sign up for the MIT Comm Lab, who knows about the Comm Lab? Has everybody heard about the Comm Lab? This is the communications laboratory where they will help you with your writing. Okay, if you do that, we'll automatically give you a 2-day extension, okay, on any of the homeworks or project write-ups or what have you. Okay, so you can, but for that you have to make an appointment with them at least a week in advance. So you got to know that you're going to get the extension for it. In addition, you cannot get an extension more than 2 days on any single assignment. Okay, it becomes impossible for us to collect the things and get them graded and so forth when we have things straggling in at the end. Good. If you do miss deadlines, et cetera, you need to go to S-Cube to let us know, and we'll try to work things out. Okay, generally, we try to work things out, especially if we know about things early, if it turns out that there's some extenuating circumstance, okay? Then there is the Comm Lab. You can read about the Comm Lab and what the kind of extensions are. There's 10 homeworks throughout the semester. They will give you hands-on experience with the tools and so forth. And the recitations are really an opportunity to have support while you're working on the homeworks. Okay, so the recitations and the homeworks actually overlap in that you will be working on homework problems during recitations. 2 quizzes, they're in class, they're closed book, but we allow you to have a crib sheet. I've found crib sheets are great because they have people do study preparation. It's a good focus for study. Most of the course is on the projects. There are 4 projects. Each project has a beta release and a final release. And the beta release, except for the 4th project, which has 2 betas, okay, because that's the big project. Generally, you can read about what the content is. One of the things that we do is we, as part of the project, we have got volunteers from industry to do code and design reviews with you of your code. So we call them the MIT Posse, It stands for Masters in the Practice of Software Systems Engineering. By far the best acronym I ever invented. Okay, so the MIT Posse deputies will help you review your code and teach you good coding practices. They're senior people. Please be nice to them. It's required that you have your code reviewed that comes in. So generally what will happen is we'll have a beta deadline. Then you will meet with your MIT Posse people who will give you some suggestions about the quality of your code. And then there'll be a final deadline for the project. So so as we go into project structure, basically, you know, a large part of the grade is how fast does it run, but it's also got to be correct. So if it doesn't do what it's supposed to do, that's not very fast. Okay, it's fast but correct. This is a fixed scale that we grade on. You're not competing with each other for performance. Okay, you're competing against a standard that we set and which we'll inform you about. When all the projects are done as teams, the first 3 projects are done in teams of 2, and then the last project is done as typically a team of 4. And we can make modifications. Sometimes we end up, if things don't pair up exactly, we'll have, you know, that number may vary a little bit, but generally it's 2 and 4. In order to make sure that we don't have problems with teams, because that's often an issue, we're going to ask you to do a very simple contract with the other members of your team to show that you've talked with them and you agree about how the project is going to be run, what the expectations are. It's really not good if one person says, you know, all I need is a pass in this class, and the other one's saying, I'm gunning for an A. That could be an incompatibility. You should talk about that up front, okay? And that's the notion of the contract. Some of the questions are here. How will you communicate? What if somebody decides to drop the class? What obligations do they have to their teammates? Like telling them? Okay, would be a good idea that you agree to that. How are you going to divide work? How are you going to review it and manage the code branches? And what do you do if some team members want to put in different amounts of time on the project? Okay, how are you going to handle that? Okay, you're encouraged to write more than that. In addition, each week we will ask for a brief 1-paragraph report on where you spent the time during the week. Okay, so it's due on Thursday, I believe, and it's just a very, very simple, here's what I did, and we're actually, I think, going to provide you a tool to make it easy to log the commits that you've made to the code base. Typically, the main thing you'll do is do a beta submission. It focuses on getting a correct implementation and a good set of tests, and to make it go as fast as you can. And then after we have the betas, we then publish all of the beta code anonymously, together with the performance of everything. So you can go in and look to see, how did that team do that did better than I did? Okay, what tricks did they do that I didn't do? Okay, and then you're allowed to incorporate those tricks in your final thing or invent new tricks to make things go fast. Okay, and then once everybody's done it, we then once again publish all the code anonymously for the end. We also, for the final, we give a benchmark of saying, if you get at least this performance, you get full marks. If you get faster than that, then you receive the adulation of your peers. Okay, but you don't get any more credit for it. Okay, okay, but if you get less than that, then there'll be a curve for how much partial credit did you get on it. Yeah.
The full marks for the final submissions, is that benchmark based on like someone's beta submission, or is it just?
No, based on their. No, it's based on one number for the whole class.
Yeah, but is
Okay.
that for like the fastest beta submission? Because that's what I've heard from years past. Is it like,
We usually are aggressive beyond. You got to do. Usually there's some additional beyond the beta. Sometimes we have had cases where we've set the mark. Where some of the people who did the beta well enough don't have to do any more work, but that's rare. I think that's happened maybe once or twice. Okay? Yeah, question?
What's the protocol for documenting like borrowed tactics?
So there will be a write-up, And then in the write-up, you should say, and in your documentation, internal documentation of your code, you can put it there as well. Okay? We'll get there in a minute. So the write-ups, should say, essentially what you did to get the performance. And the write-ups are usually due the day, is it 1 day after or 2 days after? 1 day after the code. So, push to get the code done. Don't worry about getting the write-up done. Next day, write up what you did. Yeah.
And the write-ups are individual? Are they also?
The write-ups are individual, although there's usually a part that's kind of joint. Okay? Generally, with the exception of the code review part of the project grade, generally you'll get the same grade on the joint project. Okay? So the team gets 1 grade. If there's a reason, for example, somebody didn't contribute and we can document that and so forth, then of course we will modify that. But for the most part, everybody in the project gets the same grade. So one of the things to do there is, which is really important, is make sure that the commits of your code to the Git repository are balanced among your team members. So we're going to do a lot of pair programming, and so it's important that you take turns who commits what, okay? Just so that the count is reasonable, okay? It's not reasonable to come and have no commits and say, well, everything was committed by my friend when we did pair programming. No, you have to work out a scheme whereby you both are able to do commits, okay? If you feel a team member's not pulling his or her weight, let us know, okay, as soon as possible. Also, if you suspect that your team member has vanished, let us know, and we will compensate. We hold your hands very, very well in this class, at least historically. Right, TAs? Okay. Okay. Academic honesty. I encourage you to read the thing about academic honesty. The main thing is that cheating is bad, if you didn't know that. We try to say things. It is perfectly fine if you're going to share code. It's fine to share code on Piazza, typically short snippets. It's fine to look at other code, but normally if you look at other code, you cannot copy the code verbatim. And we use some tools to discover when that has happened that are actually pretty smart tools. They can tell, whether you've done a rote substitution of variable names or whatever. There's a lot of clues in code beyond just, what the actual text is. But it's perfectly fine to put something up on Piazza and say, look at this neat thing I found, and that'll count towards your participation grade, okay? Because we want this to be community learning as much as possible. You're not competing with each other, okay? So helping other people, that's a good thing, okay? But you still have to do your own work, okay? And so we tell you things. Also, if you need help, we are here ready to help. We expect that you do try to make a reasonable attempt on your own first. We have office hours 4 days a week, okay, for 3 hours. So there's an opportunity to go there and have somebody sit and help debug your code if you're having trouble or learn something more about things and so forth. And this is a really fun class. People who take it give us good, I don't know if anybody does anybody look at those ratings? Yeah, we do okay. Okay, we do okay. It is a fun class. It is a bunch of work, but it is really fun. It's fun teaching too, by the way, because the material here is just fantastic. Okay, it is so much. It's so fun to just sort of say things, and that's what I want to get to. So, any questions about Administrivia? You can, and recitation tomorrow. You can ask more questions about that of your TAs. But I'd be happy. But I really want to get into the content. Okay, really want to get into the content. Is that good? Any other questions? Okay. As I say, also, we try to be accessible. Julie and I will be here after class, happy to take questions and so forth if anybody wants to explore things at greater depth or what have you. Okay, good. So I want to I want to give you an example of performance engineering of a very well-studied problem, namely matrix multiplication. Who has never seen this problem? Yeah. Okay, so we got some jokers in the class, I can see. Okay. This is, it takes n-cubed operations because you're basically computing n-squared dot products. Okay, so essentially, if you add up the total number of operations, it's about 2n cubed because there is essentially a multiply and an add for every pair of terms that need to be accumulated. Okay, so it's basically 2n cubed. We're going to look at it assuming for simplicity that our n is an exact power of 2. Okay, now the machine that we're going to look at is going to be one of the ones that you'll have access to in AWS. Okay, it's a compute optimized machine which has a Haswell microarchitecture running at 2.9 gigahertz. There are 2 processor chips for each of these machines and 9 processing cores per chip, so a total of 18 cores. So that's the amount of parallel processing. It does two-way hyperthreading, which we're actually going to not deal a lot with. Hyperthreading gives you a little bit more performance, but it also makes it really hard to measure things. So generally, we will turn off hyperthreading, but the performance that you get tends to be correlated with what you get when you hyperthread. For floating point unit, it is capable of doing 8 double precision operations, that's 64-bit floating point operations, including a fused multiply add per core per cycle. Okay? So that's a vector unit. So basically, each of these 18 cores can do 8 double precision operations, and so including a fused multiply add, which is actually 2 operations. Okay, the way that they count these things. Okay, it has a cache line size of 64 bytes. The iCache is 32 kilobytes, which is 8-way set associative. We'll talk about some of these things. If you don't know all the terms, it's okay. We're going to cover most of these terms later on. It's got a Dcache of the same size. It's got an L2 cache of 256 kilobytes. And it's got an L3 cache, or what's sometimes called an LLC, last level cache, of 25 megabytes. And then it's got 60 gigabytes of DRAM. So this is a honking big machine. Okay? This is like, you can get things to sing on this, okay? If you look at the peak performance, it's the clock speed times 2 processor chips times 9 processing cores per chip, each capable of, if you can use both the multiply and the add, 16 floating point operations, and that goes out to just short of a teraflops. Okay, 836 gigaflops. Okay, so that's a lot of power. Okay, that's a lot of power. These are fun machines, actually. Okay, especially when we get into things like the game playing AI and stuff that we do for the 4th project. You'll see it. They're really fun to have a lot of compute. Okay. Now, here's the basic code. This is the full code for Python for doing matrix multiplication. Now, generally in Python, you wouldn't use this code because you just call a library subroutine that does matrix multiplication. But sometimes you have a problem. I'm going to illustrate with matrix multiplication, but sometimes you have a problem that is for which you have to write the code. And I want to give you an idea of what kind of performance you get out of Python. Okay? In addition, somebody has to write, if there is a library routine, somebody had to write it, and that person was a performance engineer because they wrote it to be as fast as possible. And so this will give you an idea of what you can do to make code run fast. Okay? So when you run this code, so you can see that the start time, before the triply nested loop, right here, before the triply nested loop, we take a time measurement, and then we take another time measurement at the end, and then we print the difference. And then that's just this classic triply nested loop for matrix multiplication. And so when you run this, how long does this run for, you think? Any guesses? Let's see. How about, let's do this. Runs for 6 microseconds. Who thinks 6 microseconds? How about 6 milliseconds? How about 6 milliseconds? How about 6 seconds? How about 6 minutes? Okay. How about 6 hours? How about 6 days? Okay. Of course, it's important to know what size it is. This is 4096 by 4096 as it shows in the code. Okay? So, and those of you who didn't vote, wake up, let's get active. This is active learning. Put yourself out there. Okay? It doesn't matter whether you're right or wrong. There'll be a bunch of people who got the right answer, but they have no idea why. Okay? So it turns out it takes about 21,000 seconds, which is about 6 hours. Okay? Amazing. Is this fast? Yeah, right, duh, right? Is this fast? No, how do we tell whether this is fast or not, okay? What should we expect from our machine? So let's do a back-of-the-envelope calculation of how many operations there are and how fast we ought to be able to do it. We just went through and said what are all the parameters of the machine. So there are 2 n-cubed operations that need to be performed. We're not doing Strasson's algorithm or anything like that. We're just doing straight triply nested loop. So that's 2 to the 37th floating point operations. Okay? The running time is 21,000 seconds. So that says that we're getting about 6.25 megaflops out of our machine when we run that code. Okay? Just by dividing it out. How many floating point operations per second do we get? We take the number of operations, divide it by the time. Okay? The peak, as you recall, was about 836 gigaflops. Okay? And we're getting 6.25 megaflops. Okay? So we're getting about 0.00075% of peak. Okay? This is not fast. Okay? This is not fast. So let's do something really simple. Let's code it in Java rather than Python. Okay? So we take just that loop. The code is almost the same. Okay, it's a triply nested loop. We run it in Java. Okay? And the running time now, it turns out, is about just under 3,000 seconds, which is about 46 minutes. The same code. Python, Java. Okay, we got almost a 9 times speed up over just simply coding it in a different language. Okay? Well, let's try C. That's the language we're going to be using here. What happens when you code it in C? It's exactly the same thing. Okay? We're going to use the Clang LLVM 5.0 compiler. I believe we're using 6.0 this term. Is that right? Yeah. Okay, I should have rerun these numbers for 6, but I didn't. So now it's basically 1,100 seconds, which is about 19 minutes. So we got then about, it's twice as fast as Java and about 18 times faster than Python. Okay, so here's where we stand so far. Okay, we have the running time of these various things. Okay, and the relative speed up is how much faster it is than the previous row. And the absolute speed up is how it is compared to the first row. And now we're managing to get now 0.014% of peak. So we're still slow. But before we go and try to optimize it further, like, why is Python so slow and C so fast? Does anybody know? Okay, that's kind of on the right track. Anybody else have any articulate a little bit why Python is so slow? Yeah.
When you write like multiply and add, those aren't the only instructions Python's doing. It's doing lots of code for like going through Python objects like integers and blah blah blah.
Yeah. Okay, good. So the big reason why Python is slow and C is so fast is that Python is interpreted and C is compiled directly to machine code. And Java is somewhere in the middle because Java is compiled to bytecode, which is then interpreted and then just in time compiled to machine code. So let me talk a little bit about these things. So interpreters, such as in Python, are versatile but slow. It's one of these things where they said, we're going to take some of our performance and use it to make a more flexible, easier to program environment. Okay? The interpreter basically reads, interprets, and performs each program statement and then updates the machine state. So it's not just, it's actually going through and each time reading your code, figuring out what it does, and then implementing it. So there's like all this overhead compared to just doing its operations. So interpreters can easily support high-level programming features, and they can do things like dynamic code alteration and so forth at the cost of performance. So typically the cycle for an interpreter is you read the next statement, you interpret the statement, you then perform the statement, and then you update the state of the machine, and then you would fetch the next instruction. Okay? And you're going through that each time, and that's done in software. Okay? When you have things compiled to machine code, it goes through a similar thing, but it's highly optimized just for the things that machines are done. Okay? And so when you compile, you're able to take advantage of the hardware interpreter of machine instructions, and that's much, much lower overhead than the big software overhead you get with Python. Now, JIT is somewhere in the middle, what's used in Java. JIT compilers can recover some of the performance. In fact, it did a pretty good job in this case. The idea is when the code is first interpreted, it's executed, it's interpreted, and then the runtime system keeps track of how often the various pieces of code are executed. And whenever it finds that there's some piece of code that it's executing frequently, it then calls the compiler to compile that piece of code. And then subsequent to that, it runs the compiled code. So it tries to get the big advantage of the of performance by only compiling the things that are necessary, for which it's actually going to pay off to invoke the compiler to do. Okay. So anyway, so that's the big difference with those kinds of things. One of the reasons we don't use Python in this class is because the performance model is hard to figure out. Okay? C, it's much closer to the metal, much closer to the silicon. Okay? And so it's much easier to figure out what's going on in that context. Okay? But we will have a guest lecture where we're going to talk about performance in managed languages like Python. So it's not that we're going to ignore the topic, but we will learn how to do performance engineering in a place where it's easier to do it. Okay? Now, one of the things that a good compiler will do is, once you get to, let's say we have the C version, which is where we're going to move from this point, because that's the fastest we got so far, is it turns out that you can change the order of loops in this program without affecting the correctness. Okay, so here we went, for I, for j, for k, do the update. Okay, we could do for I, for k, for j, do the update, and it computes exactly the same thing. Or we could do for k, for j, for I, do the updates. Okay, so we can change the order without affecting the correctness. Okay, and so do you think the order of loops matters for performance? Duh. This is like this leading question. Yeah, question.
Maybe for cache localities.
Yeah. So and you're exactly right. Cache locality is what it is. So when we do that, we get the loop order affects the running time by a factor of 18. Whoa, just by switching the order. Okay, what's going on there? Okay, what's going on? So we're going to talk about this in more depth. So I'm just going to fly through this because this is just sort of showing you the kinds of considerations that you do. So in hardware, there are each processor reads and writes main memory in contiguous blocks called cache lines. Okay, previously accessed cache lines are stored in a small memory called cache that sits near the processor. When the processor accesses something, if it's in the cache, you get a hit, that's very cheap, okay, and fast. If you miss, you have to go out to either a deeper level cache or all the way out to main memory. That is much, much slower, and we'll talk about that kind of thing. So what happens for this matrix problem is the matrices are laid out in memory in row major order. That means you take, you have a two-dimensional matrix. It's laid out in the linear order of the addresses of memory by essentially taking row 1, and then after row 1, stick row 2, and after that, stick row 3, and so forth, and unfolding it. There's another order that things could have been laid out. In fact, they are in Fortran, which is called column major order. Okay, so it turns out C and Fortran operate in different orders. Okay, and it turns out it affects performance, which way it does it. So let's just take a look at the access pattern for order I, J, K. Okay? So what we're doing is, once we figure out what I and what J is, we're going to go through and cycle through K. And as we cycle through K, okay, Cij stays the same for everything. We get, for that, excellent spatial locality because we're just accessing the same location every single time. It's going to be in cache. It's always going to be there. It's going to be fast to access C. For A, what happens is we go through in a linear order, and we get good spatial locality, but for B, it's going through columns, and those points are distributed far away in memory. So the processor is going to be bringing in 64 bytes to operate on a particular datum, okay? And then it's ignoring 7 of the 8 floating point words on that cache line, and going to the next one. So it's wasting an awful lot, okay? So this one has good spatial locality in that it's all adjacent, and you would use the cache lines effectively. This one, you're going 4,096 elements apart. It's got poor spatial locality, okay? And that's why, and that's for this one. So then if we look at the different other ones, this one, the order IKJ, it turns out you get good spatial locality for both C and B, and excellent for A. Okay, and if you look at even another one, you don't get nearly as good as the other one. So there's a whole range of things. Okay, this one you're doing optimally badly in both. Okay, and so you can just measure the different ones, and it turns out that you can use a tool to figure this out, and the tool that we'll be using is called CacheGrind. And it's one of the Valgrind suites of caches. And what it'll do is it'll tell you what the miss rates are for the various pieces of code. Okay, and you'll learn how to use that tool and figure out, oh, look at that. We have a high miss rate for some and not for others. So that may be why my code is running slowly. Okay? So when you pick the best one of those, okay, we then got a relative speed up of about 6.5. So what other simple changes can we try? There's actually a collection of things that we could do that don't even have us touching the code. What else could we do for people who've played with compilers and such? Hint, hint. Yeah?
You could change the compiler flags.
Yeah, change the compiler flags, okay? So Clang, which is the compiler we'll be using, provides a collection of optimization switches. And you can specify a switch to the compiler to ask it to optimize. So you do -O and then a number. And 0, if you look at the documentation, it says do not optimize. 1 says optimize. 2 says optimize even more. 3 says optimize yet more, okay? In this case, it turns out that even though it optimized more in 03, turns out 02 was a better setting, okay? This is one of these cases. It doesn't happen all the time. Usually 03 does better than 02, but in this case, 02 actually optimized better than 03. because the optimizations are, to some extent, heuristic. Okay? And there are also other kinds of optimization. You can have it do profile-guided optimization, where you look at what the performance was and feed that back into the code, and then the compiler can be smarter about how it optimizes. And there are a variety of other things. So with this simple technology, we now, choosing a good optimization flag, in this case O2, we got for free basically a factor of 3.25, okay, without having to do much work at all, okay? And now we're actually starting to approach 1% of peak performance. We got 0.3% of peak performance, okay? So what's causing the low performance? Why aren't we getting most of the performance out of this machine? Why do you think? Yeah. Yeah, we're not using all the cores. So far, we're using just one core. And how many cores do we have? 18. Right? 18 cores. 18 cores just sitting there. 17 sitting idle while we are trying to optimize one. Okay. So multi-core. So we have 9 cores per chip, and there are 2 of these chips in our test machine. So we're running on just one of them, so let's use them all. To do that, we're going to use the Silk infrastructure, and in particular, we can use what's called a parallel loop, which in Silk you call Silk4. And so you just relay that outer loop, for example, in this case, you say Silk4, it says, do all those iterations in parallel. Compiler and runtime system are free to schedule them and so forth, okay? And we could also do it for the inner loop, okay? And, you know, it's like, or it turns out you can't also do it for the middle loop, if you think about it, okay? So I'll let you do that as a little bit of a homework problem. Why can't I just do a Silk4 of the inner loop, okay? So the question is, which parallel version works best? So we can do parallel the I loop, we can parallel the J loop, and we can do I and J together. You can't do K just with a parallel loop and expect to get the right thing, okay? So, and that's this. So if you look, wow, what a spread of running times, right? Okay, if I parallelize just the I loop, it's 3.18 seconds. And if I parallelize the J loop, it actually slows down, I think, right? And then if I do both I and J, it's still bad. I just want to do the out loop there. This has to do, it turns out, with scheduling overhead. And we'll learn about scheduling overhead and how you predict that and such. So the rule of thumb here is parallelize outer loops rather than inner loops, okay? And so when we do parallel loops, we get an almost 18x speed up on 18 cores, okay? So let me assure you, not all code is that easy to parallelize, okay? But this one happens to be. So now we're up to, what, about just over 5% of peak. Okay, so where are we losing time here? Okay, why are we getting just 5%? Yeah?
So another area for parallelism that we're not doing much of yet is instruction parallelism. So we could for example, vectorize the multiplication.
Yep, good. So that's one, and there's one other that we're not using very effectively. Okay, that's one, and those are the 2 optimizations we're going to do to get a really good code here. So what's the other one? Yeah? That's actually related to the same question, okay? But there's another completely different source of opportunity here. Yeah?
We could also do a lot better on our handling of cache misses.
Yeah, okay, we can actually manage the cache misses better, okay? So let's go back to hardware caches, and let's restructure the computation to reuse data in the cache as much as possible, because cache misses are slow and hits are fast, and try to make the most of the cache by reusing the data that's already there, okay? So let's just take a look. Suppose that we're going to just compute one row of C, okay? So we go through one row of C. That's going to take us, since it's a 4,096 long vector there, that's going to basically be 4,096 writes that we're going to do. Okay, and we're going to get some spatial locality there, which is good. But we're basically doing, the processor's doing 4,096 writes. Now to compute that row, okay, I need to access 4,096 reads from A. Okay, and I need all of B. Okay, because I go each column of B, okay, as I'm going through to fully compute C. Do people see that? Okay, so I need to just compute one row of C, I'm going to compute, I need to access one row of A and all of B. Okay, because the first element of C needs the whole first column of B. The second element of C needs the whole second column of B. Once again, don't worry if you don't fully understand this, because right now I'm just ripping through this at high speed. We're going to go into this in much more depth in the class, and there'll be plenty of time to master this stuff. But the main thing to understand is you're going through all of B. Then I want to compute another row of C. I'm going to do the same thing. I'm going to go through one row of A and all of B again. So that when I'm done, we do about 16 million, 17 million memory accesses total. Okay, that's a lot of memory accesses. So what if instead of doing that, I do things in blocks? Okay, so what if I want to compute a 64 by 64 block of C rather than a row of C? So let's take a look at what happens there. So remember, by the way, this number, 17 million, okay, because we're going to compare with it. Okay, so what about to compute a block? So if I look at a block, that is going to take me 64 by 64, also takes 4,096 writes to C, same number, okay? But now I have to do about 200,000 reads from A, because I need to access all those rows, okay? And then for B, I need to access 64 columns of B, okay? And that's another 262,000 reads from B, okay, which ends up being 500,000 memory accesses total, okay? So I end up doing way fewer accesses, okay, if those blocks will fit in my cache, okay? So I do much less to compute the same size footprint if I compute a block rather than computing a row, okay? Much more efficient. Okay, and that's a scheme called tiling. And so if you do tiled matrix multiplication, what you do is you bust your matrices into, let's say, 64 by 64 submatrices, and then you do two levels of matrix multiply. You do an outer level of multiplying of the blocks using the same algorithm, and then when you hit the inner, to do a 64 by 64 matrix multiply, I then do another 3 nested loops. You end up with 6 nested loops, okay? And so you're basically, busting it like this. And there's a tuning parameter, of course, which is, how big do I make my tile size? If it's S by S, what should I do at the least there? Should it be 64? Should it be 128? Should it be, what number should I use there? How do we find the right value of, S, this tuning parameter? Okay? Ideas of how we might find it? Yeah. You could do that. You might get a number, but who knows what else is going on in the cache while you're doing this?
Just test a bunch of them?
Yeah, test a bunch of them. Experiment. Okay? Try them. See which one gives you good numbers. And when you do that, you get, it turns out that 32 gives you the best performance, okay, for this particular problem. Okay? So you can block it, and then you can get faster. And when you do that, you now end up with, that gave us a speed of about 1.7. Okay, so we're now up to what? We're almost 10% of peak. Okay? The other thing is that if you use CacheGrind or a similar tool, you can figure out how many cache references there are and so forth. And you can see that, in fact, it's dropped quite considerably when you do blocked, the tiling versus just the straight parallel loops. Okay? So once again, you can use tools to help you figure this out and to understand the cause of what's going on. Well, it turns out that our chips don't have just one cache. They've got 3 levels of caches, okay? There's L1 cache, okay? And there's data and instructions. So we're thinking about data here for the data for the matrix. Then it's got an L2 cache, which is also private to the processor, and then a shared L3 cache. And then you go out to the DRAM. You also can go to your neighboring processors and such. Okay, and they're of different sizes. You can see they grow in size, 32 to 250, 32 kilobytes, 256 kilobytes to 25 megabytes to main memory, which is 60 gigabytes. So what you can do is, if you want to do 2-level tiling, okay, you can have 2 tuning parameters, S and T. And now you get to do, you can't do binary search to find it, unfortunately, because it's multidimensional. You kind of have to do it exhaustively. And when you do that, you end up with 9 nested loops, okay? But of course, we don't really want to do it. We have 3 levels of caching, okay? Can anybody figure out the inductive number? For 3 levels of caching, how many levels of tiling do we have to do? This is a gimme, right? 12, good, 12, okay? Yeah, you can do 12, okay. That really, and man, you know, when I say the code gets ugly when you start making things go fast, okay, right? This is like, okay. Okay, but it turns out there's a trick. You can tile for every power of 2 simultaneously by just solving the problem recursively. So the idea is that you do divide and conquer. You divide each of the matrices into 4 submatrices, okay? And then if you look at the calculations you need to do, you have to solve 8 subproblems of half the size and then do an addition, okay? And so you have 8 multiplications of size n over 2 by n over 2 and 1 addition of n by n matrices, and that gives you your answer. But then, of course, what you're going to do is solve each of those recursively. Okay? And that's going to give you essentially the same type of performance. Here's the code. I don't expect that you understand this, but we've written this using in parallel, because it turns out you can do 4 of them in parallel. And the silk spawn here says, go and do this subroutine, which is basically a subproblem. And then while you're doing that, you're allowed to go and execute the next statement, which will do another spawn, and finally this. And then this statement says, but don't start the next phase until you finish the first phase. Okay, and we'll learn about this stuff. Okay, when we do that, we get a running time of about 93 seconds, which is about 50 times slower than the last version. We're using cache much better, but it turns out, you know, nothing is free, nothing is easy in typically in performance engineering. You have to be clever. What happened here? Why did this get worse, even though, turns out if you actually look at the caching numbers, you're getting great hits on cache. I mean, you have very few cache misses, lots of hits on cache, but we're still slower. Why do you suppose that is? Let me get some of it. Yeah. Yeah, the overhead to start up the function, and in particular, the place that it matters is at the leaves of the computation, okay? So what we do is we have a very small base case. We're doing this overhead all the way down to n equals 1. So there's a function called overhead even when you're multiplying 1 by 1. So hey, let's pick a threshold, and below that threshold, let's just use a standard, you know, good algorithm for that threshold. And if we're above that, we'll do divide and conquer, okay? So, so what we do is we call if we're less than the threshold, okay, we call a base case, and the base case looks very much like just ordinary matrix multiply, okay? And so when you do that, you can once again look to see what's the best value for the base case, and it turns out in this case, I guess it's 64. Okay, we get down to 1.95 seconds. I didn't do the base case of 1 because I tried that, and that was the one that gave us terrible performance. Sorry, 32. Oh yeah, 32 is even better, 1.3. Good, yeah, so we picked 32. I think I even, oh, I didn't highlight it, okay. I should have highlighted that on the slide. So, so then when we do that, we now are getting 12% of peak, okay? And we're doing, if you count up how many cache misses we have, you can see that, you know, here's the data cache for L1, and with parallel divide and conquer, it's the lowest, but also now so is the last level caching. Okay, and then total number of references is small as well. So divide and conquer turns out to be a big win here. Okay. Now the other thing that we mentioned, which was we're not using the vector hardware. All of these things have vectors that we can operate on. Okay. They have vector that process data in what's called SIMD fashion, which means single instruction stream, multiple data. That means you give one instruction and it does operations on a vector. Okay, and as we mentioned, we have 8 floating point units per core, which we can also do a fuse multiply add. Okay, so so each vector register hold multiple words. I believe in the machine we're using this term, it's 4 words? I think so. Okay. But it's important when you use these, you can't just use them willy-nilly. You've got to have all the, you know, you have to operate on the data as one chunk of vector data. You can't, you know, have this lane doing of the vector unit doing one thing and a different lane doing something else. They all have to be doing essentially the same thing, the only difference being the indexing of memory. Okay? So when you do that, you can, so already we've actually been taking advantage of it, but you can produce a vectorization report by asking for that, and it'll tell you, the system will tell you what kinds of things are being vectorized, which things are being vectorized, which aren't, and we'll talk about how you vectorize things that the compiler doesn't want to vectorize. Okay? And in particular, most machines don't support the newest sets of vector instructions, so the compiler uses vector instructions conservatively by default. So what you, if you're compiling for a particular machine, you can say use that particular machine. And here's some of the vectorization flags. You can say use the AVX instructions. If you have AVX, you can use AVX2. You can use the fuse multiply add vector instructions. You can give a string that tells you the architecture that you're running on that special things. And you can say, well, use whatever machine I'm currently compiling on, okay? And it'll figure out which architecture is that, okay? Now, floating point numbers, as we'll talk about, turn out to have some undesirable properties, like they're not associative. So if you do A times B times C, how you parenthesize that can give you 2 different numbers. And so if you give a specification of a code, typically the compiler will not change the order of associativity because it says, I want to get exactly the same result. But you can give it a flag called fastmath, -f fastmath, which will allow it to do that kind of reordering, okay, if it's not important to you that it be the same as the default ordering, okay? And when you use that, so in particular using architecture native and fastmath, we actually get about double the performance out of vectorization, just having the compiler vectorize it, okay? Yeah, question?
So are the integers here, are the data types in our matrix, are they 32-bit?
They're 64-bit. Yep. So we use, these days, 64-bit is pretty standard. They call that double precision, but it's pretty standard, unless you're doing AI applications, in which case you may want to do lower precision arithmetic.
So float and double are both the same?
No, float is 32. Okay, so generally people use 60, and who are doing serious, linear algebra calculations use 64 bits. But sometimes they can use, sometimes they can use less, and then you can get more performance if you discover you can use fewer bits in your representation. We'll talk about that too. Okay. So the last thing that we're going to do is there are, you can actually use the instructions, the vector instructions yourself rather than rely on the compiler to do it. And there's a whole manual of intrinsic instructions that you can call from C that allow you to do, the specific vector instructions that you might want to do it. So the compiler doesn't have to figure that out. And so, and you can also use some other more insights to do things like you can do pre-processing, and you can transpose the matrices, which turns out to help, and do data alignment, and there's a lot of other things, and using clever algorithm for the base case, okay? And so you do more performance engineering. You think about what you're doing, you code, and then you run to test. And that's one nice reason to have the cloud, because you can do tests in parallel. So it takes you less time to do your tests in terms of your, sitting around time when you're doing something. You say, oh, I want to do 10 tests. Well, let's spin up 10 machines and do all the tests at the same time. When you do that, and the main one we're getting out of this is the AVX intrinsics, we get up to 0.41 of peak, so 41% of peak, and get about 50,000 speed up, okay? And it turns out that's where we quit, okay? And the reason is because we beat Intel's professionally engineered math kernel library at that point, okay? There's a good question is why aren't we getting all of peak? And, I invite you to figure that out, okay? It turns out, though, Intel MKL is better than what we did because we assumed it was a power of 2. Intel doesn't assume that it's a power of 2. And they're more robust, and although we win on the 496 by 496 by 4096 matrices, they win on other sizes of matrices. So it's not all things. So, but the end of the story is that what have we done? We have just done a factor of 50,000. Okay, if you looked at the gas economy, okay, of a jumbo jet, okay, and getting the kind of performance that we just got in terms of miles per gallon, you would be able to run a jumbo jet on a little Vespa scooter or whatever type of scooter that is, okay? That's how much we've been able to do it. You generally, let me just caution you, won't see the magnitude of a performance improvement that we obtained for matrix multiplication, okay? That turns out to be one where it's a really good example because it's so dramatic, but we will see some substantial numbers. And in particular, in 6172, you'll learn how to print this currency of performance all by yourself so that you don't have to take somebody else's library. You can, say, oh, no, I'm going to engineer that. Let me mention one other thing. In this course, we're going to focus on multi-core computing. We are not, in particular, going to be doing GPUs or file systems or network performance. In the real world, those are hugely important, okay? What we found, however, is that it's better to learn a particular domain, in particular this particular domain. People who master multi-core performance engineering, in fact, go on to do these other things and are really good at it, okay? Because you've learned the sort of the core, the basis, the foundation, okay? So we talk about doing some of these other things in a more advanced class, but we haven't done that yet. So, just a word for that for the most part, we're going to be doing multi-core performance engineering. Any questions? And then, okay, so remember, recitation tomorrow, go to any of the 4 recitations on that sheet, and we'll see you. I'll see you next Tuesday. Hey, Billy.
It was a terrific first lecture.